2008. Turian 64, 2005, /X2, 2006. 40-bit AMD 64, except some Sempron processors presented as pure X86 processors. On-die memory controller hypertransport, on-die dual-core, X2, AMDV, Athlon 64 all-ins, socket 754/939/940 ORM 22004 Pentium 4, Prescott, Celeron D, Pentium D, 2005. 36-bit EM64T, enabled on selected models of Pentium 4 and Celeron D, SSE 3,2 ND Gen Net Burst Pipelining, Dual-core, on-die, Pentium D8XX, on-chip Pentium D9XX, Intel VT, Pentium 4. 6x2, socket LGA77520006 Intel Core 2 Pentium Dual Core, 2007. Celeron Dual Core, 2008, Intel 64, and LT M64T, SSSE 3, 65nm, White Dynamis Execution, Op Fusion, Macro Op Fusion in 16-bit and 32-bit mode, 12. 13, on-chip quad-core, Core 2 Quad, Smart Shared L2 Cache, Intel Core 2 Meron, 2007 AMD Phenom /2, 2008. Athlon 2, 2009, Turian 2, 2009, 48-bit monolithic quad-core, X4, /triple core, X3, SSE 4A, Rapid Virtualization Indexing, RVI, Hypertransport 3M2 plus ORM 32008 Intel Core 2, 45nm, 40-bit SSE 4.1 Intel Atom Netbook or Low Power Smart Device Processor, P54 Core Reused Intel Core i7, Core i5, 2009, Core i3, 2010, Quick Path, on-chip MCH, Clarkdale, SSE 4.2, Extended Page Tables, EPT, for virtualization Macro Op Fusion in 64-bit mode, 12. 13. Intel Xeon Bloomfield with Nehalem microarchitecture, via nano hardware-based encryption, adaptive power management 2010 AMD FX 48-bit octa-core CMT, clustered multi-thread, FMA OpenCL, M3 plus 2011 AMD APU and E-Series, Llano, 40-bit and DIPU. PCI Express 2.0 socket FM1 AMD APU-C, ENZ series, Bobcat, 36-bit low-power smart device APU Intel Core i3, Core i5, and Core i7. Sunday Bridge /Ivy Bridge, internal ring connection decoded up cache, LGA 1155 socket 2012 AMD APU of 48-bit AVX, Bulldozer series, Bulldozer Trinity and later, based APU, socket FM2 or socket FM2 plus Intel Xeon Phi, Knight's Corner, PCIe add-on card coprocessor 4Xeon based system, Menai core chip, in order P54C very wide VPU, 512-bit SSE, LRBNI instructions, 864-bit, 2013 AMD Jaguar. Athlon, Sempron, SOC, Game Console and Low Power Smart Device Processor Intel Silvermont, Atom, Celeron Pentium, 36-bit SOC, Low /Ultra Low Power Smart Device Processor Intel Core i3, Core i5 and Core i7, Haswell /Broadwell, 39-bit AVX2, FMA3, TSX BMI1, and BMI2 instructions, LGA 1150 socket 2015 Intel Broadwell U. Intel Core i3, Core i5, Core i7, Core M Pentium, Celeron, SOC, on-chip Broadwell U PCHLP, multi-chip module, 2015-2020 Intel Skylake /Kaby Lake /Cannon Lake Coffee Lake /Rocket Lake, Intel Pentium /Celeron Gold, Core i3, Core i5, Core i7, Core i9, 46-bit AVX512, restricted to Cannon Lake Wound Workstation /server variants of Skylake. 2016 Intel Xeon Phi, Knight's Landing, 48-bit Menai Core CPU and coprocessor for Xeon Systems Airmont, Atom. Based Core 2016 AMD Bristol Ridge, AMD, Pro, A6/8/10/12, integrated FCH on D, SoC. 4-socket 2017 AMD Ryzen series /AMD EPICS resamps implementation of SMT, on-chip multiple dies 2017 Jeoxin Wudaoku, KX5000, KH20000, Jeoxin's first brand new X86-64 architecture 2018-2021 Intel Sunny Cove, Ice Lake U&Y, Cypress Cove, Rocket Lake, 57-bit Intel's first implementation of AVX512 for the consumer segment. Addition of vector neural network instructions, VNNI, 2020 Intel Willow Cove Dual Ring. Tiger Lake Y/U/H, Interconnect Architecture Updated Gaussian Neural Accelerator, GNA2, New AVX512 Vector Intersection Instructions Addition of Control Flow Enforcement Technology, CET, 2021 Intel Alder Lake Hybrid Addition of Control method that has remained the basis for most x86 designs to this day. Some early versions of these microprocessors.
I was fall asleep again, sorry. Let's read we have to read page by one page. Because I have my fingers on the mount button, but when I'm close to fall asleep, my hand is pressing. Because I'm moving the mouse when the text is reading. Read only this page.
Tiger Lake Y/U/H, Interconnect Architecture Updated Gaussian Neural Accelerator, GNA2, New AVX512 Vector Intersection Instructions Addition of Control Flow Enforcement Technology, CET, 2021 Intel Alder Lake Hybrid Design with Performance, Golden Cove, and Efficiency Cores, Gracemont. Support for Oxygen 5 and DDR5 Updated Gaussian Neural Accelerator, GNA3, Era Introduction Prominent CPU Models Address Space Notable Features. History. Designers and Manufacturers. M386, released by AMD in 1991 at various times. Companies such as IBM, VIA, NEC, AMDT, STM, Fujitsu, OKI, Siemens, Cyrix, Intersil, C&T, NextGen UMC, and DM&P started to design or manufacture x86 processors, CPUs, intended for personal computers and embedded systems. Other companies that designed or manufactured x86 or x87 processors include ITT Corporation, National Semiconductor ULC System Technology, and WITC. Such x86 implementations were seldom simple copies but often employed different internal microarchitectures and different solutions at the electronic and physical levels. Quite naturally, early compatible microprocessors were 16-bit, while 32-bit designs were developed much later. For the personal computer market, real quantities started to appear around 1990 with i386 and i486 compatible processors, often named similarly to Intel's original chips. After the fully pipelined i486, in 1993 Intel introduced the Pentium brand name, which, unlike numbers, could be trademarked, for their new set of superscalar x86 designs. With the X86 naming scheme now legally cleared, other X86 vendors had to choose different names for their X86 compatible products, and initially some chose to continue with variations of the numbering scheme. IBM partnered with Cyrix to produce the 5x86 and then the very efficient 6x86, M1, and 6x86MX, ME, lines of Cyrix designs, which were the first x86 microprocessors implementing register renaming to enable speculative execution. AMD meanwhile designed and manufactured the advanced but delayed 5K86, K5, which, internally, was closely based on AMD's earlier 29K ISC design. Similar to next-gen's NX586, it used a strategy such that dedicated pipeline stages decode x86 instructions into uniform and easily handled micro-operations.
So I have to read page by page because I did make this mistake by clicking. So
method that has remained the basis for most x86 designs to this day. Some early versions of these microprocessors had heat dissipation problems. The 6x86 was also affected by a few minor compatibility problems. The NX586 lacked a floating point unit, FPU, and the then crucial pin compatibility, while the K5 had somewhat disappointing performance when it was eventually introduced. Customer ignorance of alternatives to the Pentium series further contributed to these designs being comparatively unsuccessful, despite the fact that the K5 had very good Pentium compatibility and the 6x86 was significantly faster than the Pentium on integer code. AMD later managed to grow into a serious contender with the K6 set of processors, which gave way to the very successful Athlon and Octron. There were also other contenders, such as Centaur Technology, formerly IDT, Rise Technology, and Transmeta. VIA Technology's energy-efficient C3 and C7 processors, which were designed by the Centaur company, were sold for many years following their release in 2005. Centaur's 2008 design, the VIA Nano, was their first processor with superscalar and speculative execution. It was introduced at about the same time, in 2008, as Intel introduced the Intel Atom, its first in-order processor after the 5P Pentium. Many additions and extensions have been added to the original x86 instruction set over the years, almost consistently with full backward compatibility. The architecture family has been implemented in processors from Intel, Cyrix, AMD, VIA Technologies and many other companies. There are also open implementations, such as the ZSOC platform, currently inactive. 14. Nevertheless, of those, only Intel, AMD, VIA Technologies, and DM&P Electronics hold x86 architectural licenses, and from these, only the first two actively produce modern 64-bit designs, leading to what has been called a duopoly of Intel and AMD in x86 processors. However, in 2014 the Shanghai-based Chinese company Geoxin, a joint venture between a Chinese company and VIA Technologies, began designing VIA-based x86 processors for desktops and laptops. The release of its newest 7 family, 15, of x86 processors, for example KX7000, which are not quite as fast as AMD or Intel chips but are still state-of-the-art, 16, had been planned for 2021. As of March 2022 the release had not taken place, however. 17, from 16-bit and 32-bit to 64-bit architecture. The instruction set architecture has twice been extended to a larger word size. In 1985, Intel released the 32-bit 80386, later known as i386, which gradually replaced the earlier 16-bit chips in computers, although typically not in embedded systems, during the following years. This extended programming model was originally referred to as the X86 architecture, like its first implementation, but Intel later dubbed it IA32 when introducing its unrelated IA64 architecture. In 1999-2003, AMD extended this 32-bit architecture to 64 bits and referred to it as X86-64 in early documents and later as AMD 64. Intel soon adopted AMD's architectural extensions under the name IA32E, later using the name M64T and finally using Intel 64. Microsoft and Sun Microsystems /Oracle also use term X64, while many Linux distributions and the BSDs also use the ARM64 term. Microsoft Windows, for example, designates its 32-bit versions as X86 and 64-bit versions as X64, while installation files of 64-bit Windows versions are required to be placed into a directory called AMD64.18, Basic Properties of the Architecture. The X86 architecture is a variable instruction length, primarily CISC design with emphasis on backward compatibility. The instruction set is not typical CISC, however, but basically an extended version of the simple 8-bit 8008 and 8080 architectures. Byte addressing is enabled and words are stored in memory with little-endian byte order. Memory access to unaligned addresses is allowed for almost all instructions. The largest native size for integer arithmetic and memory addresses, or offsets, is 16, 32 or 64 bits depending on architecture generation. Newer processors include direct support for smaller integers as well. Multiple scalar values can be handled simultaneously via the SIMD unit present in later generations, as described below. Immediate addressing offsets and immediate data may be expressed as 8-bit quantities for the frequently occurring cases or contexts where A-128127 range is enough. Typical instructions are therefore 2 or 3 bytes in length, although some are much longer, and some are single byte. To further conserve encoding space, most registers are expressed in opcodes using 3 or 4 bits, the latter via an opcode prefix in 64-bit mode, while at most one operand to an instruction can be a memory location. However, this memory operand may also be the destination, or a combined source and destination, while the other operand, the source, can be either register or immediate. Among other factors, this contributes to a code size that rivals 8-bit machines and enables efficient use of instruction cache memory. The relatively small number of general registers, also inherited from its 8-bit ancestors, has made a register relative addressing, using small immediate offsets, an important method of accessing operands, especially on the stack. Much work has therefore been invested in making such accesses as fast as register accesses, i.e., a one-cycle instruction throughput, in most circumstances where the accessed data is available in the top-level cache. Floating point and SIMD. A dedicated floating point processor with 80-bit internal registers, the 8087, was developed for the original 8086. This microprocessor subsequently developed into the extended 80387, and later processors incorporated a backward-compatible version of this functionality on the same microprocessor as the main processor. In addition to this, modern x86 designs also contain a SIMD unit, CSSE below, where instructions can work in parallel on 1 or 2, 1 to 8-bit words, each containing 2 or 4 floating point numbers, each 64 or 32 bits wide respectively, or alternatively, 2, 4, 8 or 16 integers, each 64, 32, 16 or 8 bits wide respectively. The presence of wide-simmed registers means that existing X86 processors can load or store up to 128 bits of memory data in a single instruction and also perform bitwise operations. Although